Right, okay, so happy to have Hanna Komlos from NYU giving this talk about nearly optimal list labeling. Hanna is a PhD student there working with Martin March-Bolton. We used to be at Rutgers together. Here she moved to NYU. All right, okay, so I guess there's not more introduction. Go.
All right, yeah, thanks a lot for the introduction. Thanks also for inviting me to speak here today and for coming. Again, my name is Hanna Komlos. I'm a fifth year PhD student at NYU working on data structures. And this talk is going to be mostly about my paper, Nearly Optimal List Labeling, which is about to appear at the upcoming FOCS. Okay, so this is joint work with a bunch of wonderful co-authors I'm lucky to work with, Michael Bender, Alex Conway, Martin Farage-Fulton, who's also my advisor, Michal Kutsi, Phil Kuzma, Michael Sachs, and Nicole Wine. For the Zoom, have I wandered off too far, or can you hear me?
I can hear you.
Great, thank you. Just let me know. All right, so the list labeling problem is a fundamental combinatorial problem that underlies a lot of data structural applications. And I think by studying it, you also end up learning about a lot of really cool algorithmic techniques. So I designed this talk to be broadly accessible to a TCS audience. So if at any point you're not with me, please feel free to interrupt and ask questions. All right, so first of all, let's get into the definition of the problem. In list labeling, we maintain n elements in sorted order in an array of size m, where m, the size of the array, is fixed, and then n changes dynamically as elements are inserted or deleted from the set. And it's sufficient constraint that n is at most some constant of m for. So we, as the algorithm, can move elements around in the array. And in fact, we may be forced to do so in order to maintain sorted order. It's supposed to be. There we go. All right, so elements are coming into the set, they're being inserted and deleted. So the one thing the algorithm really has to do is maintain sorted order. And so we may have to move elements around in order to do that. For example, here, this element key m is coming in. We have to make a move because there's no room between elements with keys L and n. And we can move other elements around if we want to. Our goal is just to minimize the cost, which is the number of elements we move per insertion or deletion. And so all the costs that I'm going to talk about in this talk are amortized number of moves per insert or delete. Okay, so any questions about the problem before I move on?
I didn't see a cost per search.
That's right. So in this problem, our cost is purely just the number of elements that we're moving. Basically, this is a primitive that we can plug into other data structural problems.
So your little example, when there were 3 empty spots and you moved one element, you did move it to the middle. Which was the obvious thing that you're trying to.
Oh, I see. Yeah, exactly. Here we're just optimizing for the number of elements we're moving. Search costs, I guess, if our array is well packed, you could imagine we're doing some sort of binary search, but we're kind of not concerned with that here. Okay, any other questions? Yeah.
When the delete happens, you wouldn't necessarily need to move anything, right?
Exactly. Yeah, so you don't have to move anything for a delete. I think what this animation is in part trying to show is that we might still do so. So we'll see a little bit later on in the talk what algorithms for this problem look like. But typically there's some kind of configurations or like balance conditions that an algorithm wants to maintain. So maybe when you've deleted an element, it's like thrown off the balance and you want to move stuff anyway. So you certainly can do that. You may not want to if you're looking to minimize your number of moves. But there's some reasons for which moving stuff preemptively might save you on future work. All right, good question. Anything else? All right, save animation is just moving now. So. Some history on this problem. It's been studied for a very long time. And in fact, it's been studied under many different names and independently reformulated and rediscovered several times. So the first example we know of is a sparse table scheme for implementing priority queues. This is by Itai, Hanna, and Rhoda in 1981. The problem was also independently formulated as a file maintenance problem, order maintenance problem, getting and maintaining balance in binary trees, and so on. And here is a slide of sample applications. I'm not going to spend a lot of time on. The purpose of this is mostly to convince you that, first of all, there's a lot of them. And also they come from some pretty diverse areas of computer science. So you have kind of classical theoretical applications here. List labeling in particular has found a lot of use for creating patch oblivious data structures. There's also theoretical as well as practical database applications. List labeling is useful for maintaining locality when you're having data structures storing things about sparse graphs. There's a physics problem up here, scheduling, etc. So the takeaway from these two sides together is that this is a very natural combinatorial problem that comes up again and again in computer science that has a lot of different uses. Okay, so even though this problem has been studied for a long time, a part of the history of the problem was a very long-standing gap between the upper and lower bounds. So the best known upper bound up until a couple of years ago was a log squared and amortized moves per element, despite type rhoda, and then there's a corresponding general lower bound of log n moves per element by Blumenach and Sachs in 2013. And you may have noticed that that's the same paper I mentioned that initially introduced the problem. So actually the algorithm that they introduced in that first formulating paper that gets log squared n was the best known upper bound for this problem for many years. So for a long time, log squared n was conjectured to be the right answer for that and various other reasons. Okay. So one of the reasons for that is that not just the problem itself was independently reformulated, but so was the log squared n algorithm. So every time the problem was studied, a kind of similar or equivalent algorithm getting a log squared upper bound was itself rediscovered as well. So this is one reason why log squared seemed like a natural right answer. Another is that corresponding log squared lower bounds were found for various natural classes of algorithms. The first of those is deterministic algorithms. So Dean Siffers and Jenks showed that log squared is tight if your algorithm is required to be deterministic. And then the other natural class of algorithms is called smooth algorithms. All right, so let's talk a little bit briefly about what those are, because this concept of smoothness or lack of smoothness you see is going to come up a lot during this talk. So in a smooth algorithm, elements are spread evenly every time we rebuild. So rebuild means whenever the algorithm decides to move elements. So it's not required to spread the entire array evenly, but it has to pick a contiguous subinterval over here and then spread the elements out, meaning that there's roughly the same number of free slots between all the elements. So why is this a natural type of algorithm? Well, if you think about what happens if you don't have smoothness, then you have an array which is going to have a lot of elements in some parts and not many elements in others. So if we had an adversarial inserter, they could just kind of hammer all their insertions into these dense spots, and where there's more inserts, we have to do more moves, and that drives up our cost. The classical algorithm with log squared that I mentioned is both deterministic and tight. So this kind of gives a lot of intuition as to why log squared was conjectured to be the right answer. So a couple of years ago, myself and some of my co-authors started looking at this. We also set out to prove a general log squared lower bound. But since a lot of us are kind of algorithms people, and specifically randomized algorithms people, we know that a faster solution, because of these lower bounds, has to be randomized and non-smooth. We also kind of in tandem, we're working on seeing if we can do a better upper bound. And that is in fact what we did. So in a FOCS paper from 2 years ago, we proved an upper bound of log to the 3 times n amortized moves per element. And necessarily that's going to be a randomized and non-smooth algorithm. Okay, just a side note here, a couple things I want to say now that we're looking at randomized algorithms. So this upper bound and all of the bounds that I'm presenting here hold an expectation. And again, that's the cost, which is the number of amortized moves per insert or delete. And also we use a kind of standard assumption for randomized data structures, which is that of an oblivious adversary. So meaning the adversary can say know the entire distribution of our data structure, but they don't know the outcome of our random coin flips. Yeah, go ahead.
What is the array size n?
Oh, like roughly speaking relative to n.
Yeah.
Yeah, so we're typically studying a regime where n is a constant multiple of n. So something like twice as many array slots as there are elements.
Okay. And the running time doesn't depend on, I mean, when everything, but it also n.
Yeah, good question. So because I'm assuming for this talk that m is a constant multiple of m, the dependence is kind of hidden in this O. You can also study the regime where m is like 1 plus epsilon times n, where like epsilon is allowed to be below 1, then you get basically a 1 over epsilon dependence here.
Your slide was explicit that m was 1 plus theta of 1,
Very good.
so I
Yes.
thought it was that.
Yeah, no, you're correct, actually. So I put the slide that way for simplicity for this talk.
Yeah.
In full generality for this problem,
We don't-
you're allowed to assume it doesn't have to be theta, it can be 1 plus epsilon. And then you would just get like a 1 over epsilon dependence in the bounds. But for here, we're gonna assume a constant factor. And in fact, in our paper, we have a reduction to kind of get from the 1 plus epsilon g to the constant. So okay, good time to stop and see if there's any more questions.
This should probably come at the end, but if the data came from a known, the inserts came from a known distribution and the deletions were random, then life would become substantially easier and it would go to log.
Excellent question. That is a good preview of some of the stuff that we're going to talk about.
Oh, okay, sorry.
Yeah, no, not at all. Yes, so if the data comes from a known distribution, life does become substantially easier, and we'll see that a little bit.
It's like
later.
sorting is
Yes.
interesting and easy.
Yeah, in fact, I think if you didn't have the random deletes, if you just said like, the offline version of this problem, I tell you where everything goes, then the problem becomes kind of trivial because you can just slot everything in its final position. So definitely knowing something about the order of something is pretty powerful, but yeah, kind of the theme of this talk is how much do we know about the distribution and how can we use that? Okay, is somebody gonna keep an eye if there's questions in the chat? Great, thank you. All right, anything else before I move on? All right, appreciate all the questions, please keep them coming. All right, so I think I was here, so yeah, this is just to say, we assume an adversary can know the distribution of our data structure. But if you think about it, such that they don't know the random coins, meaning they don't know the state of the data structure, say in a fixed instance. All right, so given that, we prove this log to the 3 halves an upper bound, which is necessarily a randomized and non-smooth algorithm. And we ourselves also prove another lower bound for a natural class of algorithms called history independent algorithms, which the algorithm this paper belongs to. So once again, I'm going to sidebar here quickly about this definition for context, but like this and smoothness, you're going to see this come up a lot later in the talk in more detail. So a data structure is history independent if its current state reveals nothing about the past history of operations beyond the items that are currently present. So this has previously been studied kind of in the security space as a property that you want to achieve in its own right. So there's various security applications where, for instance, hiding the history, such as the privacy of past users' data, is desirable. And typically the goal is to achieve history independence without an increase in cost. In this paper, we use history independence as a tool to achieve a faster algorithm. So that's, I think, a pretty cool thing where this is the first example we know of where that was done. And the way we did this is by kind of flipping the history independence paradigm on its head. So what it used to say is that by observing the state of a data structure, say an adversary gains access, they can't deduce anything about the history of operations. The way that we use it, our adversary is actually the inserter itself. So obviously they can know the entire history because they're creating it. But we kind of reverse the chain and we say by knowing the history of insertions and deletions, the adversary can't deduce anything about the state of the data structure. Meaning if we have a randomized data structure, for instance, they don't know which instance of the distribution we're in. So basically, history independence was a very useful tool, which allows us to break open kind of 40-year stall on improving the upper bound for this problem. And then we proved the lower bound showing that that was tight. So when we're approaching this recent paper, we have a new state of the art here. The gap is now between log n and log to the 3 halves n. And we have another lower bound for a natural class of algorithms. Once again, we set about now trying to prove this as a general lower bound. This time we really wanted to do it because we thought our work was so great that it's impossible that you could ever improve on it. So we really thought log to the 3 halves n was going to be the right answer here. In tandem, once again, we looked at producing a faceted algorithm that now we know from all these little routes has to be randomized, non-smooth, and dependent on history. And then once again, that's what we did. So rather than prove a log 3 halves n lower bound, we brought down the upper bound once again to O tilde log n. So we're kind of almost at the lower bound, except for a few log n factors. So this is the headline results of the latest paper, which is a list labeling algorithm with log n times log cubed and expected cost per operation. Okay, any questions before I move on? All right, so here's the outline for the talk. Kind of generally the theme of this talk is the ways in which hiding your history can help you, and then the ways in which using your history. So we're gonna kind of, for intuition, talk through a couple algorithms before we get to ours. The first is the classical log squared n algorithm. This introduces a framework and some intuition that's used in all the algorithms we study. Then I will kind of briefly at a high level describe how we used history independence to achieve log to the 3 halves n. And then we're going to think about, conversely, how depending on the history can be used to produce something even faster. So this part will be based on a prior work by Bender who on a deterministic adaptive list labeling algorithm. And then finally we'll get to ours. Okay, so first I'll introduce a common abstraction to all the algorithms that we studied, in fact, all the algorithms I know about, where we conceptualize our array as a binary tree of nested intervals. So at the top level of the root, we have the entire array, and then its two children are its left half subarray and its right half subarray. And then those two children breaking half evenly, and so on all the way down. So kind of we have one array, which you can think of the array or any of the elements in it as like existing simultaneously at all log n levels of this tree. All right. Okay, so why is this useful? For one thing, we can kind of fix an interval or a level of the tree and just focus on it. And there we only have to concern ourselves with how many elements go into the left child and how many elements go into the right child. So why is this? Because everything is sorted, so we know the relative order of the elements. If we know an element goes left, we can kind of continue this all the way down the tree and thus fully specify the array configuration. So we have some element here, it goes to the left child. We have an element here, it goes to the left child. and so on all the way down. Basically, what this says is, if I fix an interval and just focus on its left-right distribution, that's told me everything I need to know about my algorithm. And also doing so is going to be convenient both in the way that we specify our algorithms and the way that we analyze. Okay, so this is pretty important to a lot of things we're going to present, so I want to make sure it's clear. If there's any questions.
Something is clear, actually, what is, so this is a new insertion you are doing?
Yeah.
What is this purpose about?
Oh, yeah, this is an element. You can think of it as a new insertion or something that's already there, that I can just telling you where it goes, but yeah, let's say
How
it's a
did
new
you
insertion.
decide, like, what does it mean, specifying how many elements go to left or right?
So, okay, yeah, perhaps this is not the best picture. So in our interval, we can say it's split half, so half the elements go left, half the elements go right. I suppose implicit in here is that you have to search for what's your elements relative rank.
But are these empty slots or these are?
Oh, no, I'm sorry, this is just, I just wanna focus on. But
So
imagine
look,
there's elements all.
M over two, the elements go left.
Yes,
Is really all you can say.
yeah, so.
This could be a really bad split. You're gonna fix it, so that's not true. But
Exactly, so say at the top level, okay, so I have to find my elements rank. So say the rank is n over 4. And then at the top level, I know n over 2 of my elements go left. Then I know that the sum goes to the left. And then I go to the next level. I have a number of elements here, I know how many go left, how many go right, and what's my elements relative rank, and so on all the way down. So I think perhaps a better picture here rather than a single element would have been a bunch of elements. So this is just trying to get at the fact that if I recursively tell you how many are going left to right every step, I fully specify. So is that part clear if you're on the picture?
Yes, so if you give me an array of n elements, you told me 5 of them are on the left, 3 of them on the right. I know now because these are sorted out, so I can.
They're sorted,
Okay,
exactly.
so if you give me the whole thing, you just give me these numbers, I can write down this is the point.
Exactly, so you know 5 go left, you know which ones they are because they're sorted. You don't know how those distributed in the array, so you look at its child and you do this recursively. Yes, thank you.
Since you're doing this at all levels, is it equivalent to think of this as just at all the singletons, you told me which cells are occupied and which ones aren't? You can bubble this back up the tree, and because you have to keep things in sorted order, if you know which cells are occupied, you know rate.
Yeah, exactly, so basically, if I know that, I can kind of reverse this picture.
Exactly.
Yeah, perfect. Okay, anything else? All right, so now let's use this to talk about how the classical algorithm works. So in the classical algorithm, I have basically the same picture here. I've just removed the parent-child pointers for cleanliness. But you can think about this like a tree of intervals. And then at the bottom level, we have an example array with some elements in it. So the main thing the classical algorithm does is maintain an invariant that the density of any child node in this tree can only differ from the parent by a multiplicative 1 plus something like the log n factor. So why is this thing we want? Let's think about the worst case density you can get if we maintain this invariant. So at the top level, the density, by the way, I mean number of elements over number of array slots. This is a constant by the specification of our problem, really at most. So it has 2 children. Let's look at the denser child. So by this invariant, the child has density at most 1 plus over 1 log n. And then if I keep going down, looking at the denser children, what I'm going to get is a geometric series of this 1 plus 1 over log n factors going down to the bottom. So something I should have said on the previous slide is that we naturally have log n elements of this tree because we're dividing by 2 each time. So this geometric series looks like density times 1 plus 1 over log n to the log n. So I take my constants appropriately, I can assume that assure that the worst case density at the bottom is at most 1. So this means basically that I have a valid list labeling algorithm. The configuration that I want that's induced by my density constraints says that there's enough slots for elements when I get to the bottom level. So maintaining this invariant is sufficient. Now let's look at what the algorithm does when the invariant is violated. Let's say for simplicity, instead of 1 plus log n, I have 5 at the top level. So just trust me going by the elements here. This is the density, we have 0.47. And then the density of the left child over here is 1.19 times it, which is within the invariant, so this one's fine. If I go down one more level, this child has gotten much denser than the parent. So intuitively, you can kind of see that corresponds to this D through K or E through K section here, where there's a lot more elements than there are in other parts of the array. So what the algorithm does when this density constraint is violated is it goes up in the levels until it finds an interval that is within density threshold. And then does one of these smooth rebuilds. So it just spreads the elements out here. So when it does this, subject to some minor rounding conditions, the density of all the children is going to be equal to the density of the parent. So after this rebuild, we know that the invariant is satisfied. All right, so let's see why this gets us log squared. Let's think if we did a rebuild, how many element insertions would it take until we have to do another? So after the last rebalance, the parent has some number of S items, the child has half as many because we spread them evenly. And then we inserted some number R of items in order to trigger another rebuild. And we know that because we rebuilt, this condition was violated, meaning the density of the child was greater than 1 plus 1 over log n times the density of the parent. So basically, we just plug that condition in with the variables I've given you. You do some algebra, which I'm not going to go through carefully now. But just trust me that this says that we need to have inserted a roughly 1 over log n fraction of the items in the interval in order to trigger rebuilds. So then I could have touched all the elements in the interval, so I have to charge you for all S of them when I do the rebuild. I charge that to S over log n operations, giving me a log n per element amortized cost at this level. Again, I fixed an interval of the tree. And then this could happen at all log n levels, giving me log squared amortized per operation. So this was very fast and may not have made sense of its speed, but the key takeaway that I want you to have is that if we have enforced a 1 plus 1 over log n density constraint, this translates to a log n amortized cost of maintaining this variant per level of the tree. Okay, so now let's talk about how we use history independence to speed up this algorithm. So the main idea for that paper is pretty simple. If we want lower costs, we have to rebuild less. And if we want to rebuild less, we need a looser invariant to maintain. So what if instead of saying 1 plus 1 over log n, we have a 1 plus 1 over square root log n factor of density before we trigger a rebuild? Okay, so what would happen here, I could run through the same algebra on the previous slide with square root log n in place of log n, and I get a square root log n cost per level, multiply that by log n levels, gives us log to the 3 halves and total cost. Okay, so this sounds great. It's a little bit too easy. Does anybody who may have seen the next slide briefly or has a guess want to tell me what the problem with this might be? Yeah, exactly. So why was this invariant chosen in the first place? It's because I said, when I get to the bottom, I'm definitely good. I definitely have enough for everything. But you can't plug 1 plus 1 over square root log n into the same geometric series and get a constant again. You're going to get something super constant here. So what this says is that if I kind of max out this constraint, and I look at the worst case density all the way down, I have definitely more slots than I have that type superfast. So this doesn't work, this means our algorithms failed. This can't really happen. However, since we want to speed it up, we're going to kind of take that idea and massage it and bring it to work. So the intuition is just to revert to the classical solution if you have a reason that gets too dense. So we know that the classical solution deterministically there's an overflow. If we have some interval with higher density, we're going to use that balance condition there. And then if we have an interval with lower density, we can afford to use this less stringent balance condition, the one that gets the square root of log n costs, and then we do less work there. So these have log squared n costs in intervals with higher density and log 3/2 n lower density respectively. And then kind of our main limit is to show that the vast majority of the array belongs to the second category. So most of the array falls into this log to the 3/2 n expected cost. So for instance, if we were to pick a random location and insert an element there, log to the 3/2 n is going to dominate our expected cost. Okay, so we're still not done. You may be asking, well, what if I don't insert a random location? Again, I could have an adversary that's trying to drive up your cost. So since we've done a non-smooth rebalance, we have some parts of the array that are dense and sparse, not specifically they're log squared onto the 3/2 n. For a random inserter, all the insertions go into sparse areas on average, but an adversarial inserter is just going to keep hammering on one of these red regions, and then we actually haven't gained it. So you can make all of our inserts state log squared. So this is where the idea of history independence comes in. So as a reminder, in history dependence, the current state of the data structure reveals nothing about the past history of operations beyond the items that are currently present. In this labeling, since we actually don't use whatever keys the elements came in with in the first place, we really just care about the relative ranks. This means that the state of the data structure actually only depends on the number of elements that are present at any given time and nothing else. Again, here, since we have a randomized algorithm, when I say the state, everything in the distribution of states, or if you'd like, you can think about, I pick some random points, and then I have the state. So I could have a bunch of elements coming in different keys, and critically, they can come in any order. These two situations, I have the same number of elements, I get the same data structural state. So how does this help me with my algorithm? Well, it says that the adversary can't, by some clever sequence, drive up my costs by creating dense parts of the algorithms that are more expensive, because by history independence, their sequence doesn't influence the state of the data structure at all. And also with an additional idea called the random shift, history independence says that they also can't find any dense regions that we created through our non-smooth rebalance. So by history independence, I turned this non-smooth array into the situation where an adversarial insert looks like a random. An adversary is just inserting into, as far as it knows, what are uniformly random locations that are relatively cheap. Okay, so that's the previous paper. This is kind of getting at the idea of history independence being this very useful tool that unlocks progress on a long-standing problem. And now we're going to talk about the flip side. So how instead can we use the history to do even better? Okay, so once again, we're just going to fix the level of the tree and focus on one interval. And all we care about at this granularity is whether insertions are going left or right. So I'll use blue to represent insertions that go left, and orange to represent insertions that go right. Purple, these are ones that are already there. All right, so let's say temporarily I had a workload that just looked like this. So all the insertions are going to the left. Specifically, they're all going to the same location of the array. So what I would do in kind of like the classical solution that wants things to be relatively balanced and smooth is as elements come in, I gradually move elements over in order to make them. So every time this happens, I'm kind of shifting some of these existing elements to the right. And what you'll notice is that more and more of these have to be moved, and some of them have to be moved multiple times. So let's just imagine temporarily that I knew this was going to happen. So say I know that once I observe 4 inserts that go to the left, all the rest are going to go to the left. So after I move a few, I'd say, okay, I think all the rest of your insertions are going to the left. I'm just kind of going to preemptively move a bunch of stuff over and over again. So now, as these insertions come in, no additional moves are required. So these elements can go right in, and I did have to move all these elements on the right, but I only had to move them once. So kind of in aggregate, this was a lower cost solution than the one where we did things in online fashion. Okay, so obviously the world is not that nice, and I don't get to know exactly what's going to happen. So say I had a deterministic policy, like the one I just said, once I see 4 elements move to the left, I move everything. Then if I'm an adversary, I just exploit that pretty easily. So I give you 4 elements to the left, you move a bunch of stuff over, and then I say, never mind, my next element's going over the right. So now, if you're inserting over here, you're in a region that's very dense, it's going to have very high cost. And now you have to move some stuff over. Now I've seen 4 elements to the right. Maybe I say, okay, now I think all the elements are to the right. Then I move more stuff over and so on. So actually what you've seen here is something that's even higher cost than the initial classical policy that we talked about. And it was like relatively easy to defeat this kind of algorithm. Okay, so you'll see why I'm telling you about this in a second, but as for the question you had earlier, this can be useful if we restrict a certain class of workflows. So in the Bender and paper from 07, they use this to achieve log n on certain stochastic workloads. Random hammers is a class that includes the hammer I just mentioned earlier, as well as the possibility of randomly picking a location and then hammering there for a while. So basically they say, if we have one of these workloads, we adapt and preemptively move stuff in our algorithm to achieve log n error. However, obviously that's easily defeatable by an adversary. So they want to retain the general log squared and worst case cost. And so they have a limit to how much they trust these predictions. So they kind of adapt a little bit. They maintain the classical balance thresholds that achieve log squared n, so the general workloads aren't more expensive. See how am I doing on time? Oh. Okay, so now we kind of have all the pieces to talk about our algorithm. So what we do is kind of build on this idea of adapting to a workload, but we use randomization in order to make it not exploitable. So if you take any 2 words away from this talk, I want to keep randomized adaptivity. I think this is a pretty cool and exciting concept, and I'm hoping we have applications to other problems. Okay, so we took inspiration from Bender and Hu, where for certain stochastic workloads, they're able to predict effectively. There's also a more recent field of learning-oriented algorithms. Here, you assume some predictions that come from an external black box predictor that kind of gives you information as to what the future workload may look like. And then the performance of your algorithm is parameterized by the error of your prediction. So our approach is kind of a combination of both these things, but also neither. So we also use a predictor, but it doesn't come from any external source. We build it ourselves from the workloads history, like the Bender in the paper, but we do so in a way that works on any algorithm. So we have better provable worst case guarantees on general workloads, not just stochastic. Okay, so let's talk a little bit about how we do this. I'll give a kind of high-level overview of how the algorithm works. So we define what's called an adaptivity window. So this is the number of inserts that I look at when I'm doing my adapting. So we'll worry about how to pick this later, but for now, this is the sum. Okay. What I do is I observe elements going left and right over k insertions. And then my prediction is just that the same pattern is going to occur. So for the next k insertions, I assume the same thing is going to happen. And what do I do with that prediction? I use it to influence my next rebuild. So we perform a skewed rebuild away from the denser side, and we move more elements away from where insertions are going to come in order for insertions to go into the sparser neighborhood. So kind of the measure of correctness of our predictions for these examples is going to be how dense is the area that more insertions. And this is a pretty good measure because the density or sparsity of inserts corresponds to the costs in our output. Okay, so let's look at an example. Say I had the same adversarial workload from the deterministic adaptive algorithm. And say my activity window had length 4. So over 4 inserts, I look and say they're going left. Now I predict the same thing is going to happen to the next 4 inserts. And this is exactly wrong. So so far, this is exactly the same example as we already saw. So this adaptivity window performs pretty badly. Specifically, what's going on here is that I have a hammer whose period exactly matches the period on which I'm adapting, causing me to make exactly more predictions at all levels. But now let's look at different windows I could choose. So what if my window was twice as long? In this case, I'm looking at 8 inserts, and the workload is roughly balanced. And when I look at the next 8 inserts, my prediction is it's balanced, and it is. So this one performs pretty well as far as my algorithm is concerned. I am exactly correct. However, for our cost measure, I haven't succeeded in making insertions go into a sparse side because everything's balanced. They're also not going into a denser side, so I'm giving this one okay, but at least we weren't wrong. Then if I had a window that's even shorter, I'm predicting over 2 inserts, and look at the next 2 inserts. Now over here, I'm exactly correct. 2 went left and 2 are going to go left again. And this continues all the way down. So, yeah.
So when you predict, so you pick K and you predict the next K, then you will start fresh, or this next K are now used to do the next level of prediction?
We start fresh. It's not at all intuitively clear why you have to do that. In fact, we've proven you have to, but we could not get any of our algorithms to work when the prediction and adaptivity overlap. Yeah, there's some sort of, that introduces some sort of correlation and kind of when things go wrong, that kind of messes things up. But for our algorithm, we just predict, we adapt the next window, and then we start fresh. Yeah. All right, good question. So, all right, so what this example shows is that we have the same period of hammer, but when our adaptivity window is much shorter, locally, it doesn't look like an oscillating hammer, it just looks like all insertions are going to the same side. So we're able to predict effectively when we look at a shorter neighborhood in the period of the hammer. So obviously, all these numbers are unreasonable because it's hard to fit a very slide. So imagine instead of 1 and 2, we have much bigger numbers that make sense. But what this is getting at is that if I have windows that are length, a multiplicative factor shorter than the period of the hammer, the predictions often are correct. Okay, so I have a slide here because I was waiting for somebody to ask, well, how come you align them that way so that everything works out for you? What if I align them the other way? So this is essentially the exact same picture with the exact same lengths, but where my hammer started 2 insertions later, then you can see that not everything works out the same. So here in my windows before, where I was exactly right, now I'm exactly wrong. So alignment does matter. However, I've also messed up the ability of the adversary to make me make bad prediction in the top. So those ones now end up okay. And so you kind of just have to trust me that no matter how I align it, I would get a similar distribution. But in every case, I don't have a lot of these red windows. So there's not a lot of ways for the adversary to make me predict badly on any levels of this. And this is kind of the main idea behind our algorithm. So if we choose an adaptivity window deterministically, it's very easy to fool. Yes?
I think I missed this in the beginning when you mentioned it. How much does your adversary actually know here?
Oh, so the adversary just knows our distribution, which I haven't really told you what it is yet, but so if I was, say, deterministically doing one of these things, the adversary would know it exactly. What we're about to see is that I'm going to do one of these windows in randomized fashion. And so then the adversary just knows that I'm going to pick one of these windows with some probability. Yeah. Yeah, so that's exactly the point. That's why randomization helps me do adaptivity in an effective way. So while it's very easy to feed a deterministic adaptive algorithm, any workload that does so doesn't perform particularly well if I'm adapting different granularities. So if I have an adaptivity window that's much longer, then the period over which the adversary is adapting, things just kind of balance. That's okay for me. If my adaptivity window is much shorter, things look more consistent and I'm able to predict well. So you may be asking, but what if I don't have, an exactly oscillating periodic hammer? Is there something clever an adversary could do, where it's kind of mixing these distributions together in order to mess together once? Kind of surprising answer in our paper is no, it cannot. So no matter what the adversary does against a general workload, this same phenomenon holds. So kind of on average in expectation, any workload is not able to make us perform badly at many of these different windows at the same time. And this is kind of the main algorithmic idea that gets us to the faster algorithm.
I don't get why you just don't pick the first one. I mean, in all these examples show the windows and so better. So why do you want it to be that?
Well, I guess if I know it's short, then I just back and forth.
Then everything else will be okay, so there won't be any, like, if I pick the shortest possible window,
Yeah,
then your green things you won't have any, everything else will be
yeah, so if I pick the shortest possible window,
as the adversary. So,
Oh, as the
yeah,
adversary.
I try to
okay, yes, good question. I thought you or the adversary. Yes, so basically, why doesn't the adversary pick something as short as possible so that we can't go less than it? Because it turns out that that's actually really good for us. So shortest window possible means I insert over here, I insert over here, I'm kind of spreading stuff around, back and forth, and that's exactly what this labeling algorithm wants, because then things are balanced and I actually don't have to move stuff much at all. Yeah, so good question. That's in fact something I should probably add here. So yes, so that's kind of a good intuitive point is that for instance, if you took uniformly random inserts in a list labeling algorithm, I think even the classical algorithm performs with like amortized constant. So what's really good for list labeling is if you spread stuff out in an even way. So the shortest adversarial window possible, it kind of corresponds to spreading stuff back and forth. So that's also kind of why I'm talking about hammers. Once we fix an interval and we only look at left and right, there's sort of only so many things that can happen. Either you do things randomly, or you go left for a while and right for a while. Everything kind of looks like some mixture of those. So yeah, that's kind of what this is getting at. Any other questions? Yes.
So when you, in the red part, how back then costly, because you said it's going to be worse than your initial mistake algorithm.
Yes. Okay, that's a good question. Put a pin in that. I'll get to that a little bit later, although I'm not going to answer it very precisely, but intuitively not too bad overall is the answer. All right, so more or less, this is what my algorithm does. I'm not going to give you very precise numbers for any of these because there's like pages of algebra in the paper that you can refer to, or I'm happy to talk about it offline if anyone's interested. But essentially the high level of our algorithm is that we have some adaptivity into the length, like in my example, we have geometrically increasing, and then we choose those with a probability pi, and that just gives my entire list of distribution. So I learned the imbalance for those inserts, and then another key point that I haven't included in the previous examples is that when I rebalance, I don't do so in such a way as to make everything balanced and correct. I actually rebalance even more elements away from the dense side than the adversary was going to put there. So altogether, if you fix an interval, these things work out to log cube log n cost. If you're curious, I have log n, different intervals I can pick. And then each one I do for size of the interval over log squared insert. So that's where the 3 different log factors come from. And then once again, this would happen at all the log levels. And then another inspiration we take from prior work is to say, well, this doesn't deterministically work, so we can't have an algorithm that fails some of the time. So we're once again going to revert to the classical solution if my interval gets too dense. So we just say if an interval is too dense, we call it expensive, we give it log squared n cost. So kind of the main thrust is to prove again that this doesn't happen too much. And now, because we want to target even lower cost, this can't happen with probability more than 1 over log n. So this is like kind of the main technical lemma that we prove. I am running a little short on time. So, yeah, I think I'm gonna skip over some stuff here. It's kind of in the weeds. All right, so this is kind of getting it, just like putting some more numbers and more precision to the intuitive picture that you've already seen. But essentially, our main lemma and the thrust of our algorithm boils down to this picture. So if an adversary wants to punish us for a wrong guess at a level, it has to let us predict correctly at smaller sizes, this variance expectation relationship that I skipped over. And so by rebalancing with extra skew, whatever amount that we lose in the high cost, we actually make up for and then some in the low cost reading intervals. So I think your concern was whether this high cost interval could be so bad that my entire distribution is expensive. Essentially, by kind of overcompensating and moving more elements away, what we ensure by selecting the number of elements we move and the probability correctly is that when we're correct, we actually gain more in expectation than we lose from the high cost areas. Alternatively, something the adversary could do is to kind of avoid the situation by making everything look balanced. So this corresponds to the picking the really low period. Instead, this would say that all of our intervals look pretty good. And then we don't really have to do too much. So the point of this is randomized adaptivity is a heads-eye way and tails-loop situation. So we kind of box the adversary into if it wants to do something bad at one level, we're going to perform even better at other levels, or its only other alternative is to balance things out and then it's doing our work for us. All right, so remaining open questions. The big one here is these 3 log factors. So we have a general order about log n. We'd like to get rid of these log logs completely so that everything's perfectly tight. Something a bit interesting here that I didn't mention earlier with history independence is that although history independence seems like a kind of strong property, there's actually not a lot of examples for data structures where there's a physical separation between the history independent and history dependent versions. There's maybe 1 or 2 I know of that are being published at this point. However, so this would be a separation because we show the history independent lower bound and then a history dependent upper bound. However, there's like an additional technical wrinkle because of the thing I mentioned where the data structure only depends on the number of elements. It's not the full generality of the history independence definition, where you could also consider keys. So there's something additional to work out there to turn our results into a provable separation. And then I think the most exciting open question is like this idea of randomized activity. It seems pretty cool. Are there other problems where you could get a similar trade-off where the data structure can kind of win and is unexploitable in every situation? Okay, thanks very much.